Hello, everybody. Welcome back. In this video, we're going to start chapter 22, which is confidence intervals for a population mean. In the last chapter 18, we were looking at confidence intervals for population proportions. So this will be pretty similar, but also a little different. So let's go ahead and get started. So a 1 minus alpha % confidence interval for our population mean mu instead of our population proportion. If we know the population variance or the population standard deviation, we can produce a very similar result to the confidence interval for a population proportion. If you recall, our z value for the sample mean is x bar minus mu over the population standard deviation divided by the square root of n. So we can put this z value in between two other z values, right? And say for these two z values, negative z alpha over 2 and z alpha over 2, the probability that this z value is in between our confidence level, right? 1 minus alpha. So if alpha was 0.05, let's say, was equal to 95% or 0.95, that means the area under the curve, right, in between these two z values would be 0.95. Just like in the last video, right, we can rewrite the z value on the inside, just do some algebra, and we can get a formula for the confidence interval for our population mean. So that population mean would be on this left side. Right, and it looks very similar. It'd be our sample mean plus or minus that z alpha over 2 multiplied by the standard deviation, population standard deviation over the square root of our sample size, right? And again, this is kind of key here. This is when our population standard deviation, population variance is known. So we have an example here. We take a sample of 16 stocks from a large population with a mean return of 5.2%. We know that the population standard deviation is 1.5%. Find the 95% confidence interval for the mean. Oops. So in this example, we have a sample of 16 stocks, right? We need our sample size, which is given to us there, sample of 16, right? We need our sample mean. We're told, I think the question here, the wording's a little unclear. From a large population with a mean return of 5.2%, right? So is this mean return, is it from the population or is it from the sample? I didn't really word this that well, but what I intended here was we take a sample of 16 stocks with a mean return of 5.2%. So that sample mean is 5.2. We can forget about the percentages. You might be wondering, well, hey, it's a percent. Shouldn't it be a proportion? We're given that it is in fact a mean, right? The mean return could have been 5.3%, 5.4%, so on, right? We could have been given this in dollars, but because we're told it's a mean return of 5.2%, we know we're talking about a sample mean. Right, the return, the amount of money you made in a percentage form could have been any continuous variable, right? We're not given a categorical variable here, right? Did it have a return or did it lose money? Yes or no, right? That would have been a categorical variable if we were told 5.2% of our stocks from the sample of 16 returned a profit, then that would be more of a categorical variable, right? And then we are told the population standard deviation is 1.5%. So this is 1.5. So we can basically just use all of this. We're also asked for a 95% confidence interval. We've found in a different video, right, that when we're given a 95% confidence interval, this implies that alpha is equal to 0.05, right? So that z of alpha, or 0.05 divided by 2, is z of 0.025, right? So a z value, just as a refresher, right, where z of 0.025, right? This is some z value that has 0.025 area under the curve, right? And we've also seen from our other formula, the opposite is, right, we're looking for an interval, so we have two z values. So this gives us the lower z value. The positive corresponding one is 0.975, right? Because this leaves 0.95 area under the curve. And so this means if this is 0.975, that means there is 0.025 above, right? So we're looking, and this is 0.025 also. Below 0.025 plus 0.025 is 0.05, right? So there's 0.05 area under the curve outside of our interval, right? Just as a quick reminder, and we've found these z-scores in a previous video for our confidence interval for population proportions. So if you're a little unclear on any of this, go back to those videos from chapter 18. These z value, right, is plus or minus 1.96, right? This would be negative and this would be positive. This is under our mean. This is above our mean. So this is everything we need, right, for our formula. I'm just going to shorthand this as z star. Sometimes you'll see it as z star. And then we multiply that z star by the population standard deviation divided by the square root of n. So now we just can plug everything in, right? We're given pretty much everything we need for this problem. So if we do 5.2 plus or minus our 1.96, that population standard deviation is 1.5 divided by the square root of 16, which is our sample size. So just kind of doing this step by step, we still have the 5.2 plus or minus 1.96. And I'm just going to do that square root of 16 is 4, right? 4 times 4 is 16. So the square root of 16 is 4. Low on coffee and energy, just double checking myself there. So now let's do the 1.5 divided by 4. So 5.2 plus or minus 1.96. 1.5 divided by 4 is 0.375. So now if we continue on and do 5.2, and now let's take this product, 1.96 times that 0.375, and I get 0.735. And remember, this 0.735, what we've calculated all this stuff on the right, all of this is called our margin of error. So now if we add 5.2 plus 0.735, I get 5.935. And if I do 5.2 minus 0.735, I get 4.465. So this would be our 95% confidence interval for our population mean of stock returns for this population of stocks, right? So we could say we're 95% confident that the true population mean or the true population average of return from this population of stocks is between 4.465%, right? Let's put our units back in there. It's between 4.465% and 5.935%. So a good kind of application question here too, right, would be to ask, do you think this is a good stock to buy? So take a minute, think about that. If you were looking to invest in stocks, would you consider this as an option? Why or why not? So pause here and think about it. I would think that this is a good option, right? Our interval in this context, right, does not include a 0 or a negative percentage, right? So if this is the average return and it's strictly positive, we're not saying that you're guaranteed a return between this, but if 95% of all the possible confidence intervals we could calculate contain the true mean, and if we're 95% sure that this is our interval, then the fact that it is strictly positive, right, is a good sign. Obviously, you want your return on a stock when you buy it to be positive, right? It means you're making money. If this interval contained 0 or a negative number, to me, that would signify it's a little riskier, right? There's a higher chance that I might not make any money on it, or I might lose money on it, right? If this included a 0 or a negative number in this interval. So that example, we knew our population variance, right? But if we don't know our population mean, we probably also do not know our population variance or our population standard deviation, right? This is kind of getting back to the root of statistics, right? We usually don't know something or anything about our population, right? And we want to use statistics to tell us something about our population. So in that example, right, the standard deviation of the sample mean was equal to the population standard deviation over the square root of n. And we had this z formula, right, with that standard population standard deviation. And this was a z value, right? So it was followed the standard normal distribution. But now, similar to the population proportion example, we're going to use a standard error of our sample mean. And we're basically just going to swap out that population standard deviation with our sample standard deviation. Just like we swapped out the population proportion with our sample proportion in the proportion example and chapter. So we're just going to use our sample standard deviation of x over the square root of the sample size. So s of x squared is the sample variance. What we'll see mostly is s of x not squared, right, which is the sample standard deviation. So now we have a problem. Essentially, when we plug in this sample standard deviation, this is no longer follows a standard normal distribution, because the sample standard deviation fluctuates with the sample size n, right? So our sample standard deviation itself is based on the sample size. And so as our sample size, if and when our sample size changes, this creates a different and specifically, importantly, a non-normal distribution for each different sample size. Each of these distributions is called a t-distribution. We call it the t-distribution family. We'll get to this little Greek nu is what it's called. It looks like a cursive V. So we basically, instead of using a normal distribution in our z-scores, now we're going to have to use a t-distribution when we don't know our population standard deviation. And we're going to have to use something called a t-score instead of a z-score. And the t-score will come from our t-distribution. So the t-distribution, it's also a bell-shaped curve, just like the normal distribution. It also has a mean of 0, and it is symmetric about 0, just like our standard normal distribution, right? But the difference with the t family of distributions is that it has heavier tails than a normal distribution. And we'll see this on the next slide. But basically, there's more data in the tail end of our distribution, which means there's less in the center, and there's more out here on the kind of edges. However, as our sample size n gets larger and larger, the t-distribution does get closer to the standard normal curve. When our sample size is greater than or equal to 30, the t-distribution is almost normal. It's very close to the standard normal curve. And so finally, we kind of have this new element. It's called nu. This is our degrees of freedom, and it is just equal to our sample size minus 1. And the degrees of freedom indicate which specific t-distribution we will use. So now instead of having a normal distribution, right, and z-scores, we will now have to use a t-distribution. And t-scores and our t-distribution, you can see, is dependent on our sample size and the degrees of freedom. So here's a graph of a few different t-distributions. Again, you can see it's bell-shaped, unimodal, right? It looks like the normal distribution. Here, when the degrees of freedom is equal to 1, which means you have a sample size of only 2, right? The degrees of freedom is equal to sample size minus 1. So this would mean we had a sample size of 2, right? Very small. You can see that the peak of the t-distribution is lower, right? This gold orangish t-distribution, and you can see that the tail, right, the gold tail is the highest out of all of these. So this is what we mean when we say that the t-distributions have more data in their tails compared to the normal distribution. And if it's got more data in the tails, more area under the curve, under the tails, right, it's got less area under the curve in the middle, which makes sense, right? The curve is smaller here compared to our other curves and larger here. So then when you increase your sample size just by 1 and your degrees of freedom by 1, that peak gets a little higher and that tail gets a little smaller, right? It's getting closer and closer to the normal. When you increase your sample size up to 6 and your degrees of freedom to 5, right, that peak gets even taller and your tails continue to shrink, right, getting smaller and smaller. And then, you know, if you had an infinite sample size, right, infinite degrees of infinity, then this would be very, very normal, right, with much smaller tails, a higher peak, right? So that's kind of what we're, what that last slide was talking about. So we have some requirements for using the t-distribution. We have to have obtained our data from a simple random sample. The sample mean specifically must come from a simple random sample. We need a sufficiently large sample size, and there's a couple different cases here. So if you have a sample size of less than 15, then the data should be very close to a normal model. We can't use t-methods if there's strong skewness or outliers, right? If our data isn't unimodal, if it's not symmetric, and our sample size is less than 15, we can't use the t-distribution. If our sample size is at least 15, right? So if it's between 15 and less than 40, the t-method should work as long as the data is unimodal and reasonably symmetric, right? You can make a histogram to verify this. But we still should not be using our t-methods in the presence of outliers or strong skewness. So here in this case, we can be a little less normal, right? A little skewed, but not strongly skewed, and we still can't have outliers in our data either. And then finally, if we have a sample size of greater than or equal to 40, then our t-methods can be used even in the presence of strong skewness or a few outliers. And in this case, we call t-methods robust. And that goes back to this graph, right? We said that if we had a large enough sample size, large enough degrees of freedom, then our t-distribution will be close enough to normal, even right in the presence of skewness or these outliers. Okay, so now here's an updated confidence interval for our population mean with an unknown population variance. Now, instead of those z alpha over 2 values, we've got t values, right? That are going to come from our t distribution, negative and positive values, right? Still equal to our confidence level, 1 minus alpha. And you can see on the inside, we've just replaced that population standard deviation with our sample standard deviation. You can do the same sort of algebra we've done before to get a very similar formula, right, for our confidence interval. But just note now we've got a T alpha over 2 instead of our Z alpha over 2. And we're using our sample standard deviation over the square root of n instead of that population standard deviation. So the last thing we need to talk about is how to find our T alpha over 2. And this is actually a little easier, in my opinion, to do than finding a Z value. But there is a catch with it. Previously, right, for a 90% or 95% confidence interval for our population proportion, we could use the same Z value over and over, right? Whenever the problem asked us for a 90% confidence interval, we found that one specific Z value in a previous video. I believe that was plus or minus 1.645, right? So no matter what the sample or from problem to problem, as long as it asked for a 90% confidence interval, we could always use that Z value, right? The normal distribution never changed. It was always the same. Here, our T distribution fluctuates with our sample size, right? Or with our degrees of freedom. So if you see on the left side, each row has a different value for degrees of freedom. So you can see even for, let's say, a 90% confidence interval, depending on your sample size and your degrees of freedom, that T value we're going to use is going to change. So let me take a quick step back and talk about some of the differences with this T table and the Z table. In the Z table, our actual Z values were along this column here, right? And up here, when we knew our Z value and we were looking for the area under the curve, we'd come down to, 1.6. If it was 1.65, right, we'd go over to the 0.05. We would come down and find a Z value, an area under the curve, on the inside of our Z table. So the T table is almost the opposite. Instead of our Z values being on the outside and areas under the curve being on the inside, now with this T table, we have our T scores or our T values on the inside of this table, and the areas under the curve for these different kind of scenarios, whether it's one-tailed, two-tailed, the areas under the curve are up here, and they're also kind of down here, but they're displayed as confidence levels, right? Which is good for us in this use case. Hopefully it's clear that these are T values instead of areas under the curve, because we have values that are greater than 1 all the way up to very large values over here, right? And the area under the curve for a normal distribution or a T distribution is always equal to 1, right? So you can never have an area under the curve greater than 1. So hopefully that just reminds you that these are actually T values along the x-axis of our T distribution, right? So these guys are values along here, right? They are not areas under the curve. So to select one of these T values, we'll have to first find our degrees of freedom, right? To determine which row we should be using. And remember, the degrees of freedom is just n minus 1. So basically, for example, right, if our sample size was equal to 41, then our degrees of freedom would be equal to 41 minus 1, which is 40. And that would tell us to come down to this row to pick one of these t values based on our confidence level, right? So if we were asked to construct a 95% confidence interval for mu, that 95% confidence interval, we would come to this column, right? And just like our z table, we would find where that row and that column intersect, but now it's a row of degrees of freedoms and a column of confidence level. And so our t value would be 2.021 in this specific example, right? If we had a different sample size, a different degrees of freedom, we might have to use a different one of these rows. And you might notice that we can't always find the row exactly right. What if we had a sample size of 45, degrees of freedom of 44? I would recommend that we just stick with the 40, right? 40 is a lot closer to 44 than 60. It's not going to be perfect, but it should be close enough. We'll also learn how to do this on the calculator as well. All right, so in our next video, we'll look at an example of how to do this. Okay.